For the past 17 years, many hundreds of signal integrity engineers have been using our differential probes to make time and frequency domain measurements on differential traces designed into the final product form using time domain reflectometers or vector network analyzers. I'm going to provide a short history on why the first differential probe was developed and how the differential probe internal architecture has replaced the traditional interconnecting wires with a patented high bandwidth printed circuit board, the DVT FPP70 70 GHz differential probe. We'll look at the architecture of the probe and compare it to the dual wafer probe, which has been around since the 1980s. Both types have their strengths and weaknesses that benefit the measurement ecosystem when they're used appropriately. We will touch on what S-parameter measurements are stored in the VNA touchtone file, what the electric characteristics are for both types of probes, and the kind of applications where true differential probes are best used. You will see a DVT Solutions desktop probing system and its components for horizontal and vertical probing. I will list a few takeaways for you and provide you with my contact information. In 2005, we introduced the DVT 30 GigaProbes, the world's first true differential probe with no ground, a variable pitch probe, and plated with conductive diamonds to cut through any surface oxide in order to ensure repeatable, accurate measurements. Figure 1 is a sample of a differential measurement using this probe. In 2011, we collaborated with Signal Microwave, American Probe, and Global Circuits Innovative and introduced the new DVT-40 40 GHz differential probe at the DesignCon 2011 symposium. It also has the same variable pitch and conductive diamond plating. You can create differential and single-ended time domain impedance measurements and differential S-parameter measurements to 40 GHz with de-embedding applied. Figure 2 shows a time domain plot where the green insertion loss S-parameter is the accumulation of the frequency loss from the differential probe and the trace loss measurement. When the ISD DVT-40 probe model is used in the VNA, the blue trace shows the probe loss is removed from the trace measurement when de-embedding is applied. Figure 3 shows the differential and single-ended impedance measurement captured using the DVT-40 probe. By 2019, the industry demand for higher data rates over differential traces necessitated higher bandwidth differential probes. DVT Solutions, in partnership with Signal Microwave, introduced our patented fixed-pitch differential probes up to 70 GHz. In 2020, we added differential de-embedding using the Atitech Institute de-embedding ISD software, which complements the probe's hardware design through the creation of a probe model for the differential probe. A VNA uses the resulting probe model to de-embed the probe loss from the differential trace measurement and applies an algorithm that improves the probe's hardware performance and models the differential crosstalk, therefore eliminating the need for a physical ground. Our true differential probes have no amplifiers but have passive interconnects that are functionally equivalent with the differential trace found on most printed circuit boards as seen in Figure 4. The remainder of the presentation focuses specifically on the new patented DVT FFP70 70 GHz true differential probe as seen in Figure 5. This probe does not contain wires but a printed circuit board with differential 70 GHz trace conductors. Being a true differential trace, it does not require a ground probe to probe wide-pitched traces centering around 1 mm with a 70 GHz bandwidth. When a probe is used with the VNA to acquire S parameters from a differential trace, differential and dual probes acquire different sets of S parameters. So, it is important to know which probe to use for a particular measurement application. A dual wafer probe is made up of two 50-ohm wires, each wire having a ground and a signal pin at the probe tips. This probe measures the full complement of 16 single-ended S parameters, stored in a touchtone file by the VNA, as shown in Figure 7. A differential probe is optimized to measure odd-mode differential S parameters so that the VNA only acquires single-ended insertion and return loss and coupling S parameters. To view meaningful data, these single-ended S parameters must be converted to mixed-mode differential to view the SDD21, SDD11 differential insertion and return loss S parameters as shown in Figure 6. So now we're going to contrast the electrical characteristics of wafer probes available since the 1980s with the differential probe introduced in 2005 available from DVT Solutions and their sales representatives. A probe electrical characteristics are the most important thing to consider when choosing a probe. First, determine if the probe has enough bandwidth for your measurement and whether the bandwidth specification is maintained when the probe tips match the spacing of the test pads on your board. For example, if you need a 70 GHz probe to match the 1 mm test pads on your board, you must have a 1 mm probe pitch. The fundamental probe architecture of a dual wafer probe is two 50 ohm cables, and most manufacturers specify these probes as 50 ohm probes. However, they do not have electrical coupling between the two signal conductors and therefore are not true differential probes. The obvious key specification when selecting a probe to measure differential S parameters is getting a probe that can probe the same test pad pitches as the trace you need to probe. Now, the typical test pad pitch range for board probing is between 0.8 millimeters to 1.2 millimeters, or it could be a little smaller. You need to select a probe to match the test pad pitch setting at the specific bandwidth for the measurement. But if you look at a wafer probe datasheet, they usually only provide measurements for the probe bandwidth with the probe spacing between 50 micron to 250 micron. We understand from reviewing datasheets from several wafer probe manufacturers that provide a probe pitch to bandwidth specification with a probe pitch of 1000 micron or 1 millimeter, it can drop the probe bandwidth by 60%. Our differential probes are designed to measure wide pitch test pads, and the bandwidth specifications found on the datasheet is measured with a 1 millimeter pitch probe. A differential probe is ideal for characterizing differential traces on a printed circuit board. Differential probes are used to make time and frequency domain measurements of the final prototype printed circuit board product form against design specifications using visual analysis. The DVT FFP70 70 GHz probe could be used to characterize 56 GHz Nyquist S parameters for PAM4 220 gigabits encoding designs. Figure 9 illustrates using a VNA to probe a device test board and applying de-embedding to reset the VNA measurement point to measure return loss on the transceiver outputs while the chip is active. In Figure 10, we remove the semiconductor device from its characterization board. Use a VNA and a differential probe to create a de-embedding file from the device transceiver pads to the RF connectors. Reattach the device to the test board, connect a digital oscilloscope, and apply power. Load the de-embedding file into the digital oscilloscope to move the measurement to the I/O pads, thus eliminating the differential trace loss from the active measurements in the oscilloscope. All differential and non-differential probes can be connected to our modular desktop probing systems. The picture illustration is an example of a dual probe system to make time and frequency measurements for probing horizontally of a prototype of the final product design. The probe system can be configured to probe most any size test board. The individual components can be stored in a cabinet in between a design verification. To perform front side and back side vertical probing, add one of these variable vertical test fixtures to your horizontal probing system to probe both horizontal and vertical test boards. Finally, let's review features common to all differential probes. Their rugged, wide pitch probe design allows us to probe printed circuit boards. Bandwidth specifications are measured at a 1 millimeter pitch. They're a true balanced differential probe, no ground probe required. And it contains two signal-to-signal conductors and acquires differential S parameters STD21 and STD11 and stored as a touchstone file. We use the Atayatech ISD software to de-embed the probe and to solve difficult measurement applications for our customers. Thank you for listening to our story about the development of our differential probes. And again, my name is Brian Shoemaker from DVT Solutions. Please contact us if we can be of assistance.